Okay, good afternoon. In today's lecture, I will be discussing about some numerical examples on propped cantilevers. Already we have discussed how to find the prop reaction in the previous lectures. So let us see some numerical examples in today's session. The first example is this. A propped cantilever beam 3 meters long has 400 mm wide and 150 mm deep cross section. If the allowable bending stress and the deflection at the center is 45 megapascals and 2.5 mm respectively, determine the safe uniformly distributed load the cantilever can carry. Take E equal to 120 gigapascals. Young's modulus is 120 gigapascals. So here, this is the cantilever being subjected to a UDL W. So what is the safe load W that the cantilever can carry? So that the conditions given are allowable bending stress should not exceed 45 megapascals. The bending stress should not exceed 45 Newton per mm square, and deflection, maximum deflection, should not exceed 2.5 mm respectively. Okay. Determine the safe UDL to satisfy these two conditions. So we will solve one by one here. It is a propped cantilever, okay, with UDL. So how will you solve the prop reaction? First, the prop reaction, let it be P. Here the Young's modulus is given. Maximum bending stress is 45 megapascals and maximum deflection is 2.5 millimeters. The cross section of the beam 100 mm width, 150 mm depth. Okay, so we can find the moment of inertia I as BD cube by 12, and hence section modulus I by this is y delta, you call it delta maximum deflection. Here y maximum. What is y maximum? Extreme fiber distance. Okay, that gives the section modulus, which is d by 2. Y maximum is d by 2, and hence section modulus is bd square by 6. Bd cube by 12 minus d by divided by d by 2. Isn't it? Bd square by 6. Okay. So for the given span and cross section, we find the section modulus by finding first the moment of inertia BD cube by 12, and this is actually d by 2, not d by 2. This is d by 2, I by d by 2, y maximum. Okay, so section modulus is obtained as 375 into 10 cube millimeter cube. Units are cube millimeter, and maximum bending moment is WL square by 8. So using this, we will find out W. In terms of W, you will get bending moment. And maximum bending stress is obtained by using bending equation. Bending equation. We call it sigma maximum by Y. Okay. This also can be written as M by Z. This also can be written as M by Z equal to sigma maximum. M by Z equal to sigma maximum. Okay. So we know bending moment in terms of UDL. So substituting that value here and Z value, substitute that here, and maximum stress, bending stress, it is given as 45 megapascals. So we substitute that here. So using these values, 45, that is sigma maximum equal to M by Z. So which comes out to be 3W here. So W is 15 Newton per mm. That is one value satisfying the condition of maximum bending stress. Okay. Also, we find W by using other condition of maximum deflection. The second condition on deflection is given, which is 2.5 millimeters maximum deflection. So the deflection is WL power 4 by 192 EL. So using this, we find out W away, which is 20 kilonewton per meter, and the safe load satisfying this condition. Second condition, the UDL is 20 kilonewton per meter. Using maximum stress condition, the UDL is 15 kilonewton, 15 Newton per mm, 15 Newton per mm, not this one, 15 Newton per mm, or 15 kilonewton per meter, 15 kilonewton per meter. And using maximum deflection condition, the UDL is obtained as 20 kilonewton per meter. So the safe load which satisfies both the conditions is 15 kilonewton per meter. The least of these two values will be the safe load. Okay. So that's how we'll find out safe load that can be applied on propped cantilever which satisfies the given two conditions. One of maximum stress, the second of maximum deflection. Okay. Yeah. Now another example. The beam AB, 2 meters long and carrying uniformly distributed load of 15 kilonewton per meter, is resting over a similar beam CD, 1 meter long, as shown in the figure. Find the reaction at C. So here, two cantilevers actually, the beam AB and beam CD, both are cantilever beams. Actually, what happens is the beam AB, the free end of beam AB, rests on the free end of beam CD. That means B rests on C, okay, with a roller, as shown in the figure. So here we have spans given 2 meters and 1 meter. Okay, so there is a UDL of 15 kilonewton per meter on AB, and there is no load on bead CD. There is no load on the second bead CD. So the load coming from AB will be acting here. The load coming from AB will be acting on CD. So C deflects downwards. C deflects downwards. So the deflection of C and B both are equal. The deflection of B and C both are equal. Being in contact, they both deflect equally by delta C. Okay? They both deflect by the same amount delta. Now, let us consider the downward deflection of cantilever. The downward deflection of cantilever AB due to UDL when there is no support at B. Actually, B is resting on another beam, CD, at C, isn't it? Without support at B, the beam AB under the action of UDL deflects by delta 1, or here we are calling it as Y1. Let it be Y. Okay? Deflects by Y in the downward direction. Okay? That is without support, the deflection at B is Y. And it is WL power 4 by UL. WL power 4 by 8UL. Okay? That we have already seen these deflections and all. Okay? We can use that result. The deflection at the free end of a cantilever when acted upon by UDL is WL power 4 by 8UL. And substituting the values of WL, we will get Y is equal to 30 by EL. Okay? So now we will have the reaction. Actually, it is resting on CD, isn't it? It is resting on CD. So when you consider the free body diagrams CD and EB, when we consider the free body diagrams on EB, we will have the reaction in the upward direction of C. On CD, we will have the downward force RC. Okay? Isn't it? So, considering this, AB with reaction RC acting upwards, it deflects upwards. Say by, we call it delta 1. Let it be delta 1. And we know that delta 1 is equal to RC into L cube by 3U. This is again a proved result. When point load is acting at free end, the deflection is given as WL cube by 3EI. When a point load is acting at free end, the deflection delta is given as WL cube by 3EI. That result we are using here for a reaction RC acting upwards at B. The upward deflection delta 1 is given as RCL cube by 3EI. Okay, RCL cube by 3EI. And substituting L here, we will get 8RC by 3EI, this one. So net downward deflection at B will be, so due to this, delta y is the deflection downward and delta 1 is the upward deflection. So the net downward deflection is y minus delta 1, y minus delta 1. The net downward deflection at B is y, the downward deflection due to loading, minus delta 1, the upward deflection due to reaction RC. Okay, so the net downward deflection at B is given as y minus delta 1. Okay, and also for span CD, we know that RC is acting in the downward direction, okay, due to which it deflects downwards by delta 2, and we know that delta 2 is RC L cube by 3 okay, it is same, but here for span CD L is 1 meter, so delta 2 comes out to be RC into 1 cube by 3 or RC by 3 RC by 3. Okay, and this is equal to the downward deflection at B, net downward deflection at B. That is YB is equal to delta 2. YB is equal to delta 2. So already we know what is YB, net downward deflection, which is 30 by EI minus 8 RC by 3 EI, which is equal to delta 2, which is the downward deflection at C for span CD, beam CD, due to RC, okay, which is RC by 3 EI. Okay, so from this solving for RC, we will be getting RC equal to 10 kilonewtons. RC equal to 10 kilonewtons. So actually, the value of RC depends on now, by observing this, the value of RC depends on the load here, the spans of AB and C, isn't it? It depends on the load, UDL, intensity acting on AB, and also the spans AB and C. It depends on these three factors. Okay. Yeah. Now we can work out if span of AB is 1 meter and that of BCD is 2 meters. Then what will be the reaction? We can solve for it. Okay. In the same manner, we can find out what is the reaction for reaction at C. Okay, what is the reaction at C? So let us see that here. So if L is 1 meter for span AB, W being same. If L is 1 instead of 2, so it becomes 15 by 8. This becomes 15 by 8 here. Y is equal to 15 by 8 here. And RC is equal to, this is 1 here. So RC equal delta 1, we call it. What we have called it? Delta 1, upward deflection. Is it? Where did we see? Yeah, this is upward deflection due to RC. Delta 1 is RCL cube by 3 where L is the span of AB, isn't it? If it is 1 meter, then it is RC by 3 So what is YB, net downward deflection? Y minus delta. Y is 15 by 8 or 80I minus RC by 3. RC by 3. Okay. Now delta 2. What is delta 2? For span CD, delta 2 is RCLQ. Here L is 2 meters. Okay. If L is 2 meters for span CD, then it becomes 8 RC by 3 delta 2 is 8 RC by 3 and use the same condition YB equal to delta 2. So what is YB? 15 by 80I 15 by 80I minus RC by 3I is equal to 8 RC by 3. So it comes out to be 9 RC by 3I equal to 15 by 8 EI. So EI cancels. This is 3 times. So RC is 5 by 8. RC is 5 by 8 kilometers. 5 by 8 kilometers. Is this clear? Yeah, that's how we'll find out. Reaction. Okay. Yeah. One more example. Let us see. Yeah. Beam AB. This is not. This is not the problem for this. Let us consider this. So beam AC here of span 6 meters is acted upon by UDL for a length of 4 meters from A. For a length of 4 meters from A. Okay. So what will be the prop reaction? What will be the prop reaction? When it is acting throughout the length, UDL is the entire span, then P is equal to 8W L by what is prop reaction? By equating deflections, you will get downward deflection is WL power 4 by 8EI and upward deflection is PL cube by 3EI. So it gives P 3 by 8 W 3W by 3WL by 8. Here it is 3WL by 8. The prop reaction P is 3WL by 8. This is when the load is acting over entire span from A to C. But here we don't have load completely. So UDL is only up to point B, 4 meters from fixed end. Okay. In this case, what will be the deflection? Okay. So how to find the deflection? Okay. That is the problem. Now let us consider this to be the combination of cantilever with UDL from A to B plus cantilever with upward force P acting at C. Okay, and the load W is 10 kilonewton per meter. Yeah, the condition we use is the compatibility condition that we used to find prop reaction is the net deflection at point C is 0. That means due to this, we have an upward deflection delta 2, and due to this, we have a downward deflection delta 1. Okay, we make these two equal to find the prop reaction P. Delta 2 can directly be obtained as PL by 3. Okay, these are the standard cases. We need to remember this. Deflections at free end, okay, due to the point forward acting at free end. And also deflection at C due to UDL acting over entire span, it is WL power 4 by 80. That is no. But here the load is not acting up to C. So how to find out this? What we can do here, we'll find out the deflection and slope at point B, or else we can use the conjugate beam method. Okay, conjugate beam method, just like this, and we can find out deflection, right? See, this is the conjugate beam for the given beam is C. So this intensity, this is 10 into 4 total load into 4 by 2, that is 80. So 80 by EM. Okay, this is 80 by EM. Okay, and this is a parabola. Okay, the bending moment here is parabolically from B to A, and beyond B, between B and C, the bending moment is 0. Bending moment is 0. There is no load from B to C. Okay, so this will be the conjugate beam, and this is the loading for conjugate beam. The M by A diagram of the given beam will be the loading for conjugate beam. And now delta 1, the deflection at C in actual beam, is equal to bending moment at C in conjugate beam. This is the condition. So if you find bending moment in conjugate beam at C, that gives the deflection at C in actual beam, delta. So what will be the bending moment here now? You see. For this, what will be the bending moment? So this area multiplied by centroidal distance. Okay. Centroidal distance x bar. So what is this area here? For this parabola, 1/3 base 4 meters and height. This is area 80 by, and centroidal distance from C. From B it is 3/4 of base. 3/4 of base means 3/4 of 4. Okay, and from C it is 2 plus 3/4 of base 4. Okay, so 4 gets cancelled. This becomes 5, and here 320 by 3 into 5. So 1600 by 3 1600 by 3. That is delta 1. And delta 2 is no. What is delta 2? PL cube by 3. PL cube by 3. Okay. So what will you get by equating these two? by equating delta 2 and delta 1. By equating delta 2 and delta 1, that is PLQ by 3EI is 1600 by 3EI. So what is P? L is 6 meters. L is 6 meters. So 3A gets cancelled. So 1600 by 6 cube. 1600 by 6. So how much will be getting? So 25 into 60, isn't it? 1600 by 6 into 6 into 6, isn't it? Four hundred by 54. 400 by 54 or 200 by 27. And it gives around 7.4 something. So it comes out to be 7.4 kilometers.
Like, share and subscribe. Hit the bell icon for more updates.